Hello everyone. Today we will study normal approximation for binomial and Poisson distribution. Let's first of all discuss the normal approximation for binomial distribution. Consider a set S that contains only two elements, success and failure. When an element is chosen from the set, S, let P be the chance of getting success. Let P be the chance of getting success. Then we know that the chance of getting failure is 1 minus P. Next, then the random variable X represent the number of obtained success. Then the random variable X represents the number of obtained success. Then X is either 0 or 1. We are either getting 1 success or 0 success. So suppose X is either 0 or 1. Then X has a Bernoulli distribution. Since we only try once, X has a Bernoulli distribution. Since we only do the experiment once, X has a Bernoulli distribution with perimeter P. We only choose one element once, and the chance of getting success is P. X has a Bernoulli distribution. Next, let the random variable Y equal to S1 plus S2 plus Xn. Where each xi is identical to x. Then S1, S2, Sn, they are independent and identically distributed. Random variables. By the central limit theorem. By the central limit theorem we learned last class, As n approaches to infinity, y tends to a normal distribution. As n tends to infinity, as n approaches to infinity, y tends to a normal distribution. As n approaches to infinity, y tends to a normal distribution. Now, what does y represent here? Here, y equal to s1 plus s2 plus sn. And s1, s2, sn, they all represent the number of obtained success when choosing element from the set. Since y equal to s1 plus s2 plus sn, y equal to the total number of obtained success when choosing n elements from the set with replacement. And the chance for every trial, the chance of getting success is the same, O equal to p. Then we can say y has a binomial distribution. Y has a binomial distribution. So we can say y has a binomial distribution. With perimeter n and p. Since y represents the total number of obtained success when choosing n element from the set with replacement, and the chance of getting success for every trial is the same, they all equal to p. Then I can say y has a binomial distribution. So here we can see that as n tends to infinity, y tends to a normal distribution. So we can say that for a binomial distribution, with parameters, for a binomial distribution with parameters n and p, as n tends to infinity, as n approaches to infinity, the binomial distribution tends to a normal distribution. By the central limit theorem. So let's make a conclusion. For the normal approximation, for binomial distribution, then the random variable x let x be a random variable with x has a binomial distribution n and p. There's no difference. I call a random variable x or y. There's no difference. I call a random variable x or y. So let x be a random variable with x has a binomial distribution with parameters n and p. Then as n approaches to infinity, x tends to a normal distribution. with its special value of x in earlier section, we know that for binomial distribution, its special value of x is n times p, and the variance of x is n times p times 1 minus p. So since x has a binomial distribution, its special value of x is n times p. And variance of x is n times p times 1 minus p. That's the normal approximation for binomial distribution. So here we can see that as n is sufficiently large, we can use the normal distribution to approximate a binomial distribution. But for n, how big is called sufficiently large? How big is called sufficiently large? Note, in general, when n times p is greater or equal to 5, and n times 1 minus p is also greater or equal to 5, when n times p and n times 1 minus p, they are both greater or equal to 5, then the normal approximation is a good approximation. The normal approximation for the binomial distribution is good. It's a good approximation. When n times p and n times 1 minus p, if they are both greater than 5, then we can say that the normal approximation is a good approximation. Next, let me introduce normal approximation for Poisson distribution. Let's first of all consider the following. Under some fixed conditions, assume event occurs continuously. Assume events occur continuously. And the occurrence of the events are independent. And the occurrence of the events are independent. Also, at every time period, or at every place with a fixed length, at every time period or every place with a fixed length or fixed area, the average number of occurrence of the event is known. The average number of the occurrence of the events is known. Denoted by lambda prime. every time period with a fixed length, the average number of the occurrence of the events is known, denoted by lambda prime. Usually we use lambda, but here we'll use lambda for something else. Let me call lambda prime. So in a time period with a fixed length, every time period with a fixed length, suppose that's the fixed length of the time period, the average number of the occurrence of the event is known to be lambda prime. Assume the event will occur this many times in this fixed time interval. Next, we'll divide this time interval into k equal subintervals. Next, we'll divide this time interval into k equal subintervals. We divide this time interval into k equal subintervals. Next, we divide this fixed time period into k equal subintervals. Suppose that's the first interval called I1, that's the second interval called I2, that's the third interval called I3, and that's the kth interval called I sub k. We divide this time period into k subintervals, k equal subintervals. Then the average number of an occurrence of the events in each subinterval I sub I is lambda prime over k. If I divide this time period into k equal subintervals, then the average number of occurrence of the event in each subinterval will be lambda prime over k. Since there are k subintervals, I take lambda prime divided by k. The average number of the occurrence of the event in each subinterval I is lambda prime over k. Here, k is a constant. K is an integer constant. K is a constant integer. And also, we try to make each time interval, we try to make each subinterval to be relatively small. So we make k larger than lambda prime. We try to make each subinterval relatively small. So I make k greater than equal to lambda prime. We try to make each subinterval relatively small. Next, then the random variables. Si represent the actual number of an occurrence of the events in the interval I sub I, where I equal to 1, 2, 3 until infinity. So that's I equal to 1, I equal to 2, I equal to 3, I equal to k. Continue, we have that's a fixed time interval. Continue, we have I sub k plus 1, I sub k plus 2 until infinity. Then each xi they are independent random variables. Because the occurrence of an event are independent. Because the occurrence of an event are independent. So Si, they are independent random variables. And they all has Poisson distribution with lambda equal to lambda prime over k. They all have Poisson distributions, and on each interval, the average number of occurrence of an event is lambda prime over k. They all have Poisson distribution with lambda equal to lambda prime over k. Hence they are all identical. Hence Si, they are all identical. Hence Si's they are independent and identically distributed. Independent and identically distributed random variables. Since they are independent and they all have Poisson distribution with the same lambda, so they're identical. They are called independent, identically distributed random variables. Next, let the random variable y equal to S1 plus S2 plus Sn. Let the random variable y equal to S1 plus S2 plus Sn. S1 plus S2 plus Sn, say that's the nth interval. Then, by the central limit theorem, as n approaches to infinity, here we cannot use k. We cannot use S1 plus S2 plus Sk because k is a constant. We cannot take a limit for constant, so we must use Xn. As n approaches to infinity, y tends to a normal distribution. So by central limit theorem, as n approaches infinity, y tends to a normal distribution. Here, be very careful for one thing. Y equal to s1 plus s2 plus sn. The last term here, it must be x sub n. It cannot be x sub k. If we put s sub k here, then when applying the central limit theorem, we must take a limit as k approaches infinity. If we take a limit as k approaches infinity, k cannot be a constant. K must be a variable. If k is a variable, then every subinterval I sub I depends on k. If I sub I depends on k, then the random variable Si, they all depends on k. If every random variable Si depends on k, they must be dependent random variables. If they all depends on k, they must be dependent random variables. So they are not independent. We cannot apply the central limit theorem. Therefore, it must be, the last term here must be x sub n. And then we can take a limit as n approaches infinity. Then, by central limit theorem, as n approaches infinity, y tends to a normal distribution. Next, let's try to recognize what kind of probability distribution y is. Next, let's try to recognize what kind of probability distribution y is. Here, since S1, S2, Sn, they are all Poisson distributions. S1, S2, Sn, they are all Poisson distributions. They are all Poisson random variables. And y is the sum of all Poisson random variables. Y must also be a random variable. Since y is the sum of Poisson random variables, y must also be a Poisson random variable. Y is also a Poisson random variable. Since y is the sum of n Poisson random variables, y is also a Poisson random variable. Since y is a Poisson random variable, what's its perimeter lambda? What's its lambda? In an earlier section, we know that for any Poisson random variable with perimeter lambda, its expected value is always the same as lambda. For any Poisson random variable with a perimeter lambda, its expected value is always lambda. So, since y is a Poisson random variable, its expected value must be the same as lambda. So lambda here, lambda of y, equal to the expected value of y. Now, how do we find the expected value of y? We know that y equal to s1 plus s2 plus sn. So expected value of y is the expected value of s1 plus s2 plus Sn. That can be rewritten as expected value of S1 plus expected value of S2 plus expected value of x sub n. Since S1, S2, Sn, they all have Poisson distribution, so their expected value must be the same as their lambda. Since S1, S2, Sn, they all have Poisson distribution, so their expected value must be the same as their lambda. So expected value of S1 is lambda prime over k. Expected value of S2 is also lambda prime over k. Expected value of Sn is also lambda prime over k. Here, from S1, S2 to Sn, there are n terms. From S1, S2 to Sn, there are n terms. And these terms, they are all identical. For the sum of n identical terms, their sum is 1 of the term times n. I take 1 of the term times n. That's the sum. And since y also has Poisson distribution, its special value of y is the same as lambda of y. Since y also has Poisson distribution, its special value of y is lambda of y. So lambda of y equal to lambda prime over k times n. So for the random variable y, is lambda equal to lambda prime over k times n. For y, it's lambda equal to lambda prime over k times n. Since lambda prime is a positive constant, k is also a positive constant, then I can say lambda and n, they are proportional to each other. Lambda and n, they are proportional to each other. Here, lambda and n, they are proportional to each other. Which means the larger lambda, the larger n, and the larger n, the larger lambda. As n approaches infinity, lambda approaches infinity. And as lambda approaches infinity, n approaches infinity. So here we can say that for a Poisson random variable, for a Poisson distribution with perimeter lambda, as lambda approaches infinity, since lambda and n they are proportional, as lambda approaches infinity, n also approaches infinity, then the Poisson distribution tends to a normal distribution. As lambda approaches infinity, the Poisson distribution tends to a normal distribution by the central limit theorem. So as lambda approaches infinity, since lambda and n they are proportional to each other, n also approaches infinity. So y tends to a normal distribution. So the Poisson distribution tends to a normal distribution by the central limit theorem. So let's make a conclusion here. For the normal distribution, normal approximation for Poisson distribution, let x, there's no difference I call this x or y. Let x be a random variable. With x has a Poisson distribution with perimeter lambda. let x be a random variable with x has a Poisson distribution with perimeter lambda. Then, as lambda approaches to infinity, x tends to a normal distribution. With its special value of x equal to lambda. According to an earlier section, we know that for any Poisson random variable with perimeter lambda, its special value is always lambda. And the variance of x is also lambda. Variance of x is also lambda. So that means when lambda is sufficiently large, the Poisson distribution approaches to a normal distribution. But how big is called sufficiently large? How big of lambda should be? How big should lambda be? Note, in general, when lambda is greater than 20, it's considered sufficiently big enough, sufficiently large. When lambda is greater than 20, it's considered sufficiently large. So when lambda is greater or equal to 20, then the normal approximation for the Poisson distribution is a good approximation. It's considered a good approximation. When lambda is greater than 20, it's considered sufficiently large. The normal approximation for the Poisson distribution is a good approximation. Next, let's look at some examples about using normal approximation for binomial and Poisson distributions. First example, when a coin is tossed 1,000 times, find each of the following probabilities. Part A, what's the probability of getting exactly 500 heads? Part B, what's the probability that the number of obtained heads is more than 520? Part C, what's the probability that the number of obtained heads is between 470 and 490 inclusive? Let's set down a problem first. When we toss a coin, we either get head or tail. In this problem, we're looking for number of heads. So consider head represents success, tail represents failure. And when we toss a coin for every trial, the probability of getting heads is the same. When we toss a coin 1,000 times, we can consider there 1,000 trials. And the chance for every trial of getting head is the same. So we can consider this is a binomial distribution. Let's set up a problem first. Then the random variable x represent the number of obtained heads. The number of obtained heads. In this 1,000 toss. then X has a binomial distribution. With n equal to 1,000, what's P? When we toss a coin, the chance of getting head is a half, so P is half. X has a binomial distribution. With n equal to 1,000, P equal to half. According to an earlier section, we know that for any binomial random variables with parameters n and p, its expected value is always n times p, and its variance is always n times p times 1 minus p. Here, x is a binomial random variable with n equal to 1,000, p equal to half. So its expected value is always n times p, which is 1,000 times half. 1,000 times half is 500. Variance of x is always n times p times 1 minus p. Here n is 1,000, p is a half. 1 minus p is 1 minus half, that's another half. 1,000 times half, that's 250. So mu of x is the same as expected value of x equal to 500. And sigma of x is square root of the variance of x, which is square root of 250. That's the setup. Now answer the question. Part A. What's the probability of getting exactly 400 heads? What's the probability of getting exactly 400 heads? This is a binomial distribution. X is a binomial distribution. If we solve it directly, we're looking for probability that x equal to 500. The formula for binomial distribution is n choose x, p to the power of x times 1 minus p to the power of n minus x. That's the formula for binomial distribution. Here we plug in 1,000. If we plug in 1,000 for n, 500 for x, then plug in half for p, plug in 500 for x, 1 minus p, that's another half. n minus x, n is 1,000, x is 500. 1,000 minus 500 is another 500. If we try to solve this in the calculator, it won't work. Because this number, 1,000 choose 500, that's a huge number. Calculator won't work for such large numbers. So it doesn't work in the calculator. If we try to solve it directly, it doesn't work in the calculator. Since it doesn't work in the calculator, we try to find a probability using a normal approximation. We try to use a normal approximation for this binomial distribution. Before we use normal approximation for binomial distribution, let's verify two things. We must verify that n times p must be greater or equal to 5. And n times 1 minus p must be greater or equal to 5. Here, n times p is 500. In this problem, n times p is 500, which is greater than 5. N times 1 minus p, n is 1,000, 1 minus p, 1 minus half, and that's another half. 1,000 times half, that's 500. Since both n times p and n times 1 minus p, they are both greater than 5. That means if I use a normal approximation, it will be a good approximation. Here we know that when n is sufficiently large, this binomial random variable x tends to have a normal distribution. Since x has a normal distribution, we can convert x to z, the standard normal distribution. Then use a table of the standard normal CDF to find the probabilities. Let's convert x to z first. The formula for conversion is x is z equal to s minus mu over sigma. g equal to s minus mu over sigma. That's a formula for conversion. So we take 500 minus mu. Mu is also 500 over sigma. Sigma is radical 250. Here, 500 minus 500 over radical 250 is 0. What's the probability that g equal to 0? Since g is the standard normal distribution, g is a continuous random variable. Probability for any continuous random variable equal to a constant is always 0. Probability for any continuous random variable equal to a constant is always 0. Because for this probability, we take integral from a to a, f of x dx. Integral from a to a is always 0. So for any continuous random variable, probability that s equal to a is always 0. Since g is a continuous random variable, this probability is 0. Does it make sense? Does this answer make sense? We know that when we toss 1,000 coins, it's possible to have 400 heads. When we toss 1,000 coins, it's possible to have 400. It's possible to have 400 heads. So this probability is clearly not 0. So that's wrong. If we solve it like this, that's wrong. Now, how can we use normal approximation to find the probability here? Here, since x has a binomial distribution, we know that for each x in the support, there are some probabilities. For example, when x equals to 500, suppose that's its probability. I draw a bar representing its probability. The height of the bar represents its probability. The height of the bar represents probability. Suppose that's a probability when s equals to 499. And suppose that's a probability when s equals to 498. And so on. On the other side, suppose that's a probability when s equals to 501. We also the height represent probabilities. Suppose that's a probability when s equals to 502. And so on. We know that when n is sufficiently large, this binomial distribution tends to have a normal distribution. When n is sufficiently large, this binomial distribution tends to have a normal distribution. In order to find a probability using normal distribution, we try to find the probability under the curve over this bar. In order to approximate the probability, we try to find the probability under the curve over this bar for s equals to 500. We try to find the probability under the curve over this bar. Now for this probability here, we try to find area under the curve between these 2 points. What's these 2 points? This point is the midpoint of 499 and 500. This point is the midpoint of 499 and 500. So the left end point here is 499.5. The right end point is a point between 500 and 501. So that's the midpoint between 500 and 501, which is 500.1. So if we try to use normal distribution to approximate this binomial distribution, we must find the area under the curve from 499.5 and 500.5. We need to find area under the curve between 499.5 and 500.5. So if I use normal distribution to approximate binomial distribution, I need to find the area under the curve between 499.5 and 500.5. This is called the half-unit continuity correction. This is called a half-unit continuity correction. making probability that x equal to 500 equal to probability that x between 499.5 and 400.5. This is called the half-unit continuity correction. Usually, just call this continuity correction. Now, since x has a normal distribution, I can convert x to the standard normal distribution. The formula for conversion, again, is g equal to s minus mu over sigma. (499.5) minus mu. Mu is 500. Sigma is radical 250. So take 499.5 minus mu over radical 250. Then the other side is 500.5 minus mu over sigma. Sigma is radical 250. Then its calculator. Round the answer to 2 decimal places. Here I get negative 0.03 on the left side. On the right side, I get positive 0.03. Then, in order to find the probability using the table of the standard normal CDF, I must rewrite the probability in the form of probability that g is less or equal to some constant, or probability that g is less than constant. They both equal to phi of g. They both equal to phi of the constant. This probability can be rewritten as probability that g is less than 0.03 minus probability that g is less or equal to negative 0.03, which is phi of 0.03 minus phi of negative 0.03. Then use the table. Phi of 0.03. Phi of 0.03 is 0.51197. 0.51197. Phi of negative 0.03. Negative 0.03 is here. It's 0.48803. 0.48803. Next calculator. When I subtract, this is 51197. Use calculator. When I subtract, I get 0.02394. In general, for the final answer, we round to 4 decimal places. That's about 0.0239. Next, let me write down the half-unit continuity correction in detail. In general, when we use normal approximation, for any discrete random variables, to find the probability that s equal to a, we need to use half-unit continuity correction. We need to apply half-unit continuity correction. Sometimes it's just called continuity correction. which means probability that S is equal to A. If I use normal approximation, that's probability that S is between A minus half and A plus half. When we use normal approximation to approximate S probability S equal to A, I need to take a probability for S is between A minus half and A plus half. In this example here, when we try to find probability that S equal to 500 using normal approximation, I need to find probability that S is between 500 minus half and 500 plus half. This is called the half unit continuity correction. Sometimes it's also called the continuity correction. Next, let's look at part B. What's the probability that the number of obtained heads is more than 520? So part B, we're looking for probability that X is more than 520. Since binomial distribution is a discrete random variable, we need to apply continuity correction. If we apply continuity correction, what do we get? If we apply continuity correction, what do we get? Let's draw some bars represent these numbers. Let's draw some bars first. For example, 520 is here. For binomial distribution, there are some probabilities for all x in the support. Suppose there's a probability when s is 520. The height represents probability. The height of the bar represents probabilities. 521 is here. 522 is here. 519 is here. We are looking for probability that x is more than 520. That means s could be 521, s could be 522, and so on. We try to find probabilities for this area, for this part here. If I use normal approximation, we try to find area under the curve over these bars. So here, left endpoint, the left endpoint is 520.5. The left endpoint here is 520.5, and go all the way to infinity. So if I apply half unit continuity correction, that's the probability that s is greater than 520.5. When we use normal approximation to approximate binomial distribution for any discrete random variables, we need to apply half unit continuity correction. That's what we get here. Next, we need to convert x to z. Since x tends to have a normal distribution, we can convert x to z to the standard normal distribution. The formula for conversion is x minus mu over sigma. So here we use 520.5 minus mu. Mu is 500 over sigma. Sigma is 250. Sigma is not equal to 250. Then use calculator. Round the answer to 2 decimal place. Here, if I round the answer to 2 decimal place, I get 1.30. Since we try to use the table of the standard normal CDF to find probability, I try to divide the probability in the form of probability that z less or equal to some constant, or probability that z less than some constant. They both equal to phi of z. They both equal to phi of the constant. Here we have probability that z is greater than 1.30. I can use the complement. That's 1 minus probability that z is greater than z is less or equal to 130. That's 1 minus phi of 1.30. Therefore, phi of 1.30, I can find it in the table. Phi of 1.30 is 0.90320. Next calculator, I get 0.0968. That's part B. Part C. What's the probability that the number of obtained heads is between 470 and 490 inclusive? What's the probability that the number of obtained heads is between 470 and 490 inclusive? Part C, we're looking for probability that S is between 470 and 490 inclusive. That means we include the endpoint. That's the probability that S is between 470 and 490. Next, since X is a discrete random variable, we need to apply continuity correction. Since X is binomial distribution, which is a discrete random variable, we need to apply continuity correction. If I apply continuity correction, what do we get here? Let's draw some bars. Suppose that's 469. That's a probability for S is 469. That's 470. That's 471, and so on. That's 489. That's 490. That's 491. We're looking for probability that S is between 470 and 490 inclusively. Inclusively, that means we include 470 and 490. Since X tends to have a normal distribution, we're looking for probability under the curve over its bars. We're looking for probability under the curve over its bars. For this area here, the left endpoint is the point between 469 and 470. So the left endpoint is 469.5. The right endpoint is a point between 490 and 491. That's 490.5. So after continuity correction, we're looking for probability that S is between 469.5 and 490.5. That's what we get after continuity correction. Next, we need to convert X to Z to the standard normal distribution. The formula for conversion is X Z equal to S minus mu over sigma. Mu is 500. Sigma is radical 250. Mu is 490. Sigma is mu is 500. Sigma is radical 250. After conversion, it's Z. We have the standard normal distribution here. Next, find the probability. Use calculator, round each number to two decimal place. Use calculator, round each number to 2 decimal place. Here I get negative 1.93. For the number on the right side, I get negative 0.60. Use calculator, round to 2 decimal places. That's what I get here. Next, in order to use the table of the standard normal CDF, I try to run a probability in these two forms. Probability that Z less than some number or probability z less than or equal to some number, or probability z less than some number. They both equal to phi of the constant. So this can be rewritten as probability that z is less than negative 0.60 minus probability that z is less than or equal to negative 1.93. That's phi of negative 0.60 minus phi of negative 1.93. Phi of negative 0.60 in the table. Negative 0.6 is here. Negative 0.60 is here. 0.27425. 0.27425. Phi of negative 1.93. Phi of 1.93. Negative 1.93 is here. That's 0.02680. 0.02680. Then I use my calculator. The answer is 0.24745. In general, we want to answer to 4 decimal places. That's 0.2475. That's the probability that the number of obtained heads is between 470 and 490 inclusive. Next example, in a barber shop, customers visit an average rate of 4 customers per hour. Assume the barber shop opens 10 hours a day. Part A, in a given day, what's the probability that exactly 35 customers visit? Part B, in a given day, what's the probability that at least 45 customers visit? Part C, in a given day, what's the probability that the number of visiting customers is between 30 and 50 exclusive? Let's set out a problem first. We know that customers visit at an average rate of 4 customers per hour in a fixed time interval. If we know the average number of occurrence of events, we can use Poisson distribution. So, let the random variable x represent the number of visiting customers in a given day. Let x represent the number of visiting customers in a given day. Then x has a Poisson distribution. What's lambda here? What's lambda here? Visiting customers is 4 customers per hour. 4 customers per hour. Then how many customers in 10 hours? We know the barber shop open 10 hours a day. Customer visits in 4 hours, visit at a rate of 4 customers per hour. How many customers will visit in 10 hours? In the same rate. Here we can cross multiply. Lambda equal to 40. Since customers visit at a rate of 4 customers per hour, it will be 40 customers in 10 hours. So x has a Poisson distribution with lambda equal to 40. Then, in the earlier section, we know that for any random variables with Poisson distribution, its special value of x is always lambda. Variance of x is also lambda. So here, its special value of x is lambda, which is 40. Variance of x is also lambda, which is also 40. Next, find mu of x and sigma of x. Mu of x is always the same as its special value of x, which is 40. Sigma of x is square root of the variance of x, which is square root of 40. Now, let's answer the question. Part A. In a given day, what's the probability that exactly 35 customers visit? Part A. What's the probability that exactly 35 customers visit? So in part A, we're looking for probability that s equal to 35. If we try to solve it directly using Poisson distribution, what do we get? If we try to solve it directly using Poisson distribution, the formula for Poisson distribution is e raised to negative lambda times lambda raised to power of x over x factorial. Here, lambda is 40. If I plug in, I get e raised to negative 40 over lambda to the power of x. Here, x is 35 over 35 factorial. Here, if I use my calculator and round the answer to 4 decimal place, I get 0.0485. That's the exact probability. That's the exact probability. Now, if I try to use a normal approximation, what do I get? That's the exact probability. That's the answer without approximation. That's the exact probability. Now, if I try to use normal approximation for these probabilities, what do I get? First of all, this random variable x has a Poisson distribution. When we use normal approximation for Poisson distribution, we need to make sure lambda is greater than 20. When lambda is greater than 20, you will have a good approximation. Here, in this example, lambda is 40. For this random variable x, lambda is 40, which is greater than 20. So if I use normal approximation, it will be a good approximation here. So when lambda is sufficiently large, this x, by central limit theorem, this random variable x tend to have a normal approximation. If I use normal approximation for s equal to 35, I need to apply half unique continuity correction. I need to apply half unique continuity correction. If I apply half unique continuity correction for probability that s equal to 35, I need to find probability that s is between 35 minus 0.5 and 35 plus 0.5. 35 minus 0.5 is 34.5, and 35 plus 0.5 is 35.5. Since this x tend to have a normal distribution, I can convert x to the standard normal distribution, z. Let's convert x to z, the standard normal distribution. The formula for conversion is z equal to x minus mu over sigma. So here I take 34.5 minus mu. Here mu is 40. Over sigma. Sigma here is radical 40. Here I convert x to z. And then for 35.5 I use 35.5 minus mu over sigma. Next, I use my calculator. Round the answer to 2 decimal places. I get probability that z is between negative 0.87 and negative 0.71. Since we try to find probabilities using the table of the standard normal CDF, I need to rewrite the probability in the form of probability that z is less or equal to some number, or probability that z is less than some number. They both equal to phi of z. They both equal to phi of z. So this probability here can be rewritten as probability that z is less than negative 0.71 minus probability that z is less than negative 0.87. This is phi of negative 0.71, and this is phi of negative 0.87. Next, use the table of the standard normal CDF to find the probabilities. For phi of 0.71, phi of negative 0.71, Negative 0.7 is here. 1 is here. I get 0.23885. 0.23885. Next, use a table find phi of negative 0.87. Negative 0.8 is here. 7 is here. Negative 0.87 is 0.19215. 0.19215. That's phi of negative 0.87. Then I subtract. I get 0.0467. That's an approximate probability for x equal to 35. This is an approximate answer. This is an approximate answer using normal approximation. That's an approximate probability using normal approximation. We can see that this answer is very, very close to the actual probability. This answer is very close to the exact probability. So when lambda is greater than 20, it has a very good approximation. Part B, in a given day, what's the probability that at least 45 customers visit? At least 45 means 45 or more. So in part B, we're looking for probability that x is greater than or equal to 45. Here, x has a Poisson distribution. Its support is integers from 0, 1, 2 to infinity. If we try to solve it directly, we need to find f of 45 plus f of 46 plus f of 47 until infinity. It may be too much work. If you think of the complement, if you use 1 minus probability that x is less than 45, still we need to compute 1 minus f of 0 plus f of 1 plus f of 2 plus f of 44. We need to add up these 45 terms. Still, not too much work. So think of a simpler way. If we use normal approximation, it will be much, much easier. When lambda is sufficiently large, we can use normal approximation for Poisson distribution. When lambda is sufficiently large, by central limit theorem, this x tend to a normal distribution. So we can use normal approximation for this probability. If we apply normal approximation to a discrete random variable, we need to apply half-unit continuity correction. How do we apply half-unit continuity correction here? How do we apply continuity correction here? Let's draw some bars. For each x in the support, there are some probabilities. Suppose there's a probability where x equals 45. Suppose that's a probability where x equals 44. Suppose that's a probability where x equals 46. Suppose that's a probability where x equals 47, and so on. When lambda is sufficiently large, we know that Poisson distribution tends to a normal distribution. In order to use normal distribution to find the probabilities, we try to find the area under the curve over these bars. We have x is greater or equal to 45. So that's the probability we are looking for. In order to use normal approximation to approximate the area, to approximate probability, we try to find area under the curve over these bars. We try to find area under the curve over these bars. So that's the area under the curve over these bars. The endpoint here is a point between 44 and 45. The endpoint here is a point between 44 and 45. here we use the midpoint 44.5. So that's the left endpoint. Right endpoint goes to infinity. So after continuity correction, we are looking for probability that x is greater than 44.5. Here, since x tends to a normal distribution, I can convert x to the standard normal distribution. Then use the table of the standard normal PDF, standard normal CDF to find the probability. If I convert x to z to the standard normal distribution, the formula for conversion is z equal to x minus mu over sigma. So we have 44.5 minus mu. Mu is 40. Mu is 40. Sigma is vertical 40. Then use my calculator. Round to 2 decimal place. I get 0.87. I get 0.87. Now we are looking for probability that z is greater than 0.87. Since we try to use the table of the standard normal CDF to find the probabilities, I need to rewrite this probability in the form of probability that z is less or equal to z, or probability that z is less than z. They both equal to phi of this constant z. They both equal to phi of this constant z. Here we have probability that z is greater than 0.87. We can think of the complement. The complement is 1 minus probability that z is less or equal to 0.87. That's in this form. So that's 1 minus phi of 0.87. In the table, phi of 0.87 is here. 0.87 is 0.80785. It's 0.80785. Then subtract 1 minus 0.80785. I get 0.19215. In general, for the final answer, round to 4 decimal places, I get 0.1922. That's the probability that at least 45 customers visit. That's the probability that at least 45 customers visit. Part C. In a given day, what's the probability that the number of visiting customers is between 30 and 50, exclusive? Exclusive means we don't include 30 and 50. So part C, we're looking for probability that S is between 30 and 50. We don't include the endpoints. Here we can solve it directly. If we want to solve it directly, we can find f of 31 plus f of 32 plus f of 49. But still, there are 18 terms. It may still be too much work. So for a simpler way, we can try to use normal approximation. Since lambda is more than 20, it has a good approximation using normal approximation. So a simpler way is we can use normal approximation. If we use normal approximation, since x is a discrete random variable, we need to apply continuity correction. Since x is a discrete random variable, we need to apply continuity correction. So if I apply continuity correction, what do I get? We try to approximate the probability when x is between 30 and 50. We know that for discrete random variable, for all x in the support, there are some probabilities. Suppose that's 30. That's the probability when x equals 30. That's the probability when x equals 31. That's the probability when x equals 32. That's the probability when x equals 48. That's the probability when x equals 49. That's the probability when x equals 50. and so on. We are looking for probability that x is between 30 and 50, exclusive. Means we don't include 30 and 50. We start from 31, 32, until 48, 49. Since lambda is sufficiently large, x tends to a normal approximation. X tends to a normal distribution. This Poisson distribution tends to a normal distribution. In order to use normal approximation to find the probabilities, we try to find the area under the curve over these bars. We try to find area under the curve over these bars. So this area. We try to find area under the curve over these bars. And for these bars, the left endpoint here is 30.5. That's a number between 30 and 31. Left endpoint is 30.5. Right endpoint is a number between 49 and 50. That's 49.5. So after continuity correction, x is between 30.5 and 49.5. Next, we know that since lambda is sufficiently large, by central limit theorem, x tends to a normal distribution. Since x tends to a normal distribution, we can convert x to the standard normal distribution. Then find the probability using the table of the standard normal CDF. Let's first of all convert x to z, to the standard normal distribution. The formula for conversion is z equal to s minus mu over sigma. So we get 30.5 minus mu. Here, mu is 40. Sigma is radical 40. Do the same thing for 49.5. We get 49.5 minus mu over sigma. Sigma is radical 40. Then use calculator. Round this number to 2 decimal places. I get negative 1.50 and positive 1.50. In order to find a probability using the table of the standard normal CDF, I try to rewrite the probability in the form of probability that z is less or equal to z, and probability that z is less than z. They both equal to phi of z. Here, this probability can be rewritten as probability that z is less than 1.50 minus probability that z is less than negative 1.50. That's phi of 1.50. And that's phi of negative 1.50. Next, find the probability in the table. Phi of 1.50 is 0.93319. Phi of 1.50 is 0.93319. Minus phi of negative 1.50. Phi of negative 1.50. Negative 0.1 is negative 1.5 is here. 0 is here. I get 0.06681. 0.06681. Then subtract. If I subtract, I get 0.86638. And then in general, we run the answer to 4 decimal places. I get 0.8664. That's the probability that the number of visiting customers is between 30 and 50 exclusive.